Hi everyone, can everyone hear me? Is that working? Great. My name is Andrew. I work for Fastly, which is a content delivery network. But today I'm going to be talking about a particular passion of mine, which is HTTP. And HTTP is one of those things that kind of falls between the cracks. It's not a back-end technology. It's not a front-end technology. It's a networking protocol. But it's very important to us as JavaScript developers because more and more of what we do in the browser depends upon the rules and the settings that are established by the connection and by the metadata that is presented in HTTP. So in the beginning, HTTP was quite simple, and the header metadata that we exchanged on the request and the response was really used just to describe the content itself. So the date that the content was generated, the type of content that we should expect, and how much content we should expect to read. And this just helped us to understand as a browser how to interpret the content and how much content to wait for. Today, that response probably looks more like this. So it's hard not to look at this and think, did we go wrong somewhere? Or is it that actually HTTP and the web in general, the web platform in general, has gotten a lot more complicated, a lot more sophisticated, it does a lot more stuff, and there's a lot more people using it, so we need better security, we need more granular controls, and these additional pieces of metadata that have been introduced into the platform help us to do that. It's also possible that we're all copying and pasting sets of headers from Stack Overflow, and we actually don't know what any of these mean at all. So I'm hoping that it's more of the former than the latter, but some of these we'll dig into today. So another reason I'm interested in headers is that I used to be on the W3C technical architecture group. That's a group of 9 people who sort of look after the overall architecture of the World Wide Web. And every time a new standard is proposed for a web specification, it's presented to the tag for our review. So what we do is we take a very broad, high-level look at the technology, and we say, is this consistent with the way that things are done on the web? Does this have conflicts or inconsistencies with other web technologies? And then we give that feedback back to the working group that's developing that technology. And I found that, to my surprise, a lot of the things that we ended up reviewing were headers, rather than things like new elements or new JavaScript methods or DOM APIs. And I also had a conversation with Steve Souders, who is a performance expert, used to be at Google and Yahoo, now runs SpeedCurve. And he had come up with this technique for clearing objects from browser caches. So his product is a RUM, real user monitoring library, like a Google Analytics type thing, and it would be added to your website in the same way that you would add any other kind of third-party script. And he wanted to give it a really long cache lifetime, but he also wanted to be able to clear it out of everybody's browser caches whenever he released a new version. Which sounds like quite a difficult thing to do. Anyway, he developed this technique for doing it, and he said to me recently, this is really old, I did this in 2012, there must be a better way of doing it now. And I said, well, surely, Steve, you must have heard of clear site data, which clears the browser cache via an HTTP response header. And all you have to do is convince the browser to make any request to your server at all. Doesn't have to be for the object that's in the cache. In fact, it won't be, because that's the problem. And then you add this response header to that response, clear site data, cache, cookies, storage, execution, contexts. And that will destroy the browser cache. All the objects that the browser has cached for your domain will be deleted. And he said, wow, that's amazing. I've never heard of this header before. You should write a blog post about it. So I did. And when I was doing this research, I realized that actually this header is supported by no browsers. Now, fortunately, I wrote this blog post in December 2017, and it is now supported. So, that's really good news. But it made me think, once headers and you know, these kind of ideas have gone through the standards process, just how well implemented do they get and how much usage do they get in the web community? And also those headers that have gone beyond that, that have become redundant, that have gotten replaced with other things, are they still being used even though they shouldn't be? So I started looking at HTTP Archive, which is a massive database of the state of the web, which is updated every 2 weeks. It uses, it used to use the Alexa top 100 million. I think it now uses some Google data to source a list of URLs to crawl. It's about 1 million websites. So there's around 50 million requests in the database, and as I said, they rerun it every 2 weeks. You can query it just using some basic SQL, and you can put together some really interesting insights into what the web looks like. So I did that, and I graphed the most popular response headers that I saw across those 50 million responses, and started to look for things that I thought were surprising. So I want to present some of those results to you today, divided into 2 categories. The first category is the headers that we don't want. This is the stuff that we're seeing too much of on the web, and then we'll get on to the stuff that we don't see enough of. So the first header that I saw that I didn't recognize was P3P, and that's despite the fact that it's present on 1 in 10 responses in HTTP Archive. Who knows what P3P is? Show of hands? Very few people, which is a good thing. The interesting thing about the P3P header is that it's almost always set to the string, "This is not a P3P policy," which is interesting, right? Because is it a P3P policy or is it not? It turns out this is a really curious bit of internet history. It stands for Platform for Privacy Preferences Project, and it was invented by Microsoft as a way to create a machine-readable statement of privacy. So it would be a way for the website to communicate to the browser in a machine-readable way the kinds of personal data that the website was collecting and what the website was going to do with that data. Seems to me actually a really good idea and much better than what we have today with the really complicated cookie notifications and consent prompts and whatever. But it never really caught on. And the reason that it still lives is because Microsoft made it a requirement to have a P3P policy in order to access third-party cookies in iframes. So anyone that wants to do that needs to have a policy. It doesn't matter what the policy is, so they set it to "This is not a P3P policy." So this is a really good example of like artifacts of internet history that still live on even though they should have died a long time ago. So you might be thinking, well, that was a completely pointless thing for me to learn. So here's something a bit more useful. Everybody knows what the expires header is, right? Okay. 80% of responses in HTTP Archive contain an expires header. It was standardized like 22 years ago. It's supported by all browsers. What possible problem could I have with the expires header? Well, the main problem I have with it is that it's always Thursday, the 1st of December, 1994 at 4 p.m. This is by far and away the most popular value in HTTP Archive. Why? Anyone want to suggest why this is so popular? Yes, go ahead. Stack Overflow? Well, probably. But where did Stack Overflow get it from? Yes, it's in the spec. It's the example in the HTTP spec. So I have a couple of theories about why people copy the date from the spec. One is that the HTTP date format is really stupid. It includes the day of the week. So if you wanted to come up with some random date in the past in your head, you would have to know what day of the week that was in order to form a valid HTTP date. And because we can't do that, we have to go and look it up somewhere. You may as well copy the example. The other theory I have is that people think that if they want a date that's in the past because something has already expired, for some reason it needs to be a long time ago. Because the dates that I was finding in the archive are all really, really old. Now, just for your information, yesterday is just as expired as 30 years ago. So you don't need a date that's really, really old. But it seems like a lot of people do want to use very old dates. Anyway, perfectly fine to do this. If you do this, then right next to this example in the specification, you will read this text, which says, If a response includes a cache control field with the max age directive, a recipient must ignore the expires field. Now this is like kind of spec language. Recipient here means browser, field means header. You can't miss it, it's right there. So you would think that anyone that's including an expires header in their responses would not also include a cache control header with a max age directive. Only 64% actually do. So all of those responses are including a useless expires header which is not being used. And you might think, well, it's backwards compatibility, but this was standardized 22 years ago, so I think probably that's enough time to stop using the expires header. You also tend to see things like this. This is from someone who really, really doesn't want this thing to be cached. Because the cache control header has a number of directives. This is basically all of them. And the pragma header is not even a response header. It was only ever a request header. And it was part of HTTP 1. And it was deprecated in 1.1, which was 22 years ago. So we probably don't need to include that at all, and definitely not in a response. If you don't want something to be cached, you should do this. And I'll tell you why. No store tells clients not to store this object in persistent storage. So that essentially says don't cache it. But you will also want to say private if you intend the object to not be copied and used for multiple users. Because saying don't cache something is not the same as saying only use it for one person. And for networks like Fastly, we will sometimes see hundreds of requests for the same object come in at the same time. So if it takes your server 1 second to generate a response, and in that time we've had another 99 requests for the same object, then we'll wait for your response to come back to our network to figure out, like, can we use this response to satisfy all 100 requests? If we can, great. We won't send another 99 requests to your server. So to stop us from doing that, you also need to say that this response is private. It can only be used for one user. Cool. So let's move on to Xcache and a bunch of other headers that this kind of is part of a family, because Xcache doesn't exist. There's no document telling me what this is. There's no specification or standard. There's no working group that decided to create this header. It literally doesn't exist formally anywhere. And yet, 13% of domains in HTTP archive are emitting this header. And they almost all agree on what the value should be, which is the word hit. And this actually is our fault. CDNs, edge networks like Fastly or Akamai or Cloudflare or CloudFront or whatever, we add this header to indicate to our customers whether this object was a hit in our cache. And it's pretty much the only way that they're going to be able to find that out, other than through log files. But this is kind of a bad way of doing it, because what we're really doing is we're telling the end user whether something was a hit or not. We're not really telling our customer. And there's lots of other headers like this. You know, there's things like X request ID or X generator or X powered by, X served by, various other things. All of these are headers that the browser doesn't understand. So including them in the response achieves absolutely nothing. So it's worth removing them. If you're using something like Express.js, you could disable the powered by header by doing this. But a lot of the headers that you end up adding to responses typically are added after processing in Node, if you're using Node. For example, if you're using Node behind Nginx, then Nginx will add a server header. If you then send it through a CDN like Fastly, we'll add a bunch of headers as well. So it's usually the very last step in the chain where you want to unset the headers that you don't want. So if you're using varnish cache, for example, you would write this VCL to remove any of the headers that you don't want to see in the response. You could also think about making it conditional. So you could say, since some of these headers are useful for debugging, maybe we'll keep them if a certain additional thing is present, like if there's a cookie or you've set some kind of custom request header, then we'll still include those response headers. But otherwise, just get rid of them, because ordinary users don't need to see them and won't see them because, like, it's not part of the page. Okay, X-frame options. So this is a header that is pretty useful. it stops your site being framed by a site that's running on a different origin. This is typically done to prevent a security practice known as clickjacking, where your site could be made transparent and a user could be convinced to click somewhere in your page in order to commit some kind of action. There's nothing wrong with wanting to do that. The only problem is that there's a better way of doing it, which is that content security policy now has a directive called frame ancestors. If you set that to self, then it achieves essentially the same thing as X-frame options, same origin. It has two benefits. One is that you already have a content security policy, don't you? So you can add this to it. And the second is that it's better specified. The spec is more detailed, and so it's likely that the interoperability and the compatibility will be better. And finally, let's talk about via. Via is the only header I've mentioned so far that is both a request and a response header. And via is not set by browsers, and it is not set by origin servers. Via only enters into HTTP if you have a proxy in between the browser and the server. So let's use Fastly as an example. If we go from the end user through Fastly to your server, then we will add a via header to the request as it passes through. That basically just lets the origin server know that there was someone in between the eventual end user and themselves. Now this is actually very useful, because just imagine what would happen if the Fastly configuration here was set up to use another CDN as its backend, and that CDN was set up to use Fastly as a backend, and then very bad things would happen, especially because both of those parties have gigantic networks with enormous amounts of bandwidth, and you could imagine requests like bouncing backwards and forwards for a long time. So the via header stops this from happening because it says this request has already gone through this node. So if it comes back and you see it again, then you can just stop forwarding it. But that really only requires the request version of via. Why do we add another via header on the way back? Because once it's got to the origin, we know that it's not in a loop. So as it works its way back through the layers of proxies, normally only one, we really don't need to add another via header. It's not going to be seen by the end user, so you could think about removing that. So those are the headers we don't want. Let's talk about the ones that we do. And I've mentioned it already, kind of jokingly, that you all have a content security policy, because statistically it's highly likely that you don't. Only 3% of the web, according to HTTP Archive, is setting a content security policy. And there's a good reason for that, which is that it's really, really hard. The average length of a CSP is 593 bytes, and there are some quite extraordinary edge cases where they're very, very big indeed. Conceptually, CSP is really simple. And this is actually the example from the Mozilla Developer Network documentation. And this makes sense. We're saying, by default, load everything from the same origin, but you can load images from anywhere, and media and scripts can come from these specific places. That's pretty easy to understand. So we load the document from the origin server without any CSP rules, and then the CSP kicks in, and any resources that that document then loads, whether those be images or scripts or style sheets or API requests, are subject to the rules of the content security policy. So we've essentially established a firewall in the browser. The problem is that that applies to everything that your document does, including third parties, analytics, ads, everything. So you tend to find things like this. Now this, as a content security policy, is not very good. And it's not very good for a number of reasons. The one is obviously extremely obvious. It's so large that it's likely that the first packet exchanged in your TCP connection doesn't actually contain any HTML at all, because you filled it up entirely with headers. The second reason is that it is not actually offering any security at all. So let's just take a look at some of the highlights of this 9,643 byte header. It includes unsafe inline and unsafe eval. This allows a script with no origin attached to it at all to be executed in the context of the document. It also includes star.cloudfront.net. That's one of our competitors, so I can't guarantee that I could take control of a subdomain of cloudfront.net, but I think that I probably could if I signed up as a customer. I know for sure that I could upload something to tagmanager.google.com, and I think we all know that we could upload something to star.amazonaws.com. So this achieves nothing. And it's really sad to see that, this response has been stuffed up with, useless data. And this useless data is not just padding out the response, but it's actually coming ahead of anything useful. So this is in the critical path, and we should get rid of it. That said, you should have a content security policy. Just think about what it is. Don't automatically generate it. And don't consider a content security policy to be a success because it allows all your resources to load. That's not a successful CSP. A successful CSP is one that blocks requests that shouldn't happen, not one that allows requests that should happen. So, sticking with security, let's talk about strict transport security. This is a header that allows a browser to make a first connection to your website over TLS. And this is on the off chance that your end user types in your web address without typing http:// in front of it. So that's basically everyone all the time. So most of the time, if you don't have one of these headers, you will have to have a redirect because the first request will be over HTTP, your server will then redirect to HTTPS, and then the browser will issue a second request. That's bad for performance. It's also bad for security because it means that there's a window of opportunity where a middleman could take over that connection and even redirect the user to a genuinely secure site that looks like yours and is signed using a fake cert. So we need to stop that initial HTTP connection. Very simple to use, much easier than CSP. All you need is a max age. You can make it stricter with directives like include subdomains, and you can also throw in the word preload as well, which is pretty punchy. If you put preload in there, then it means that when the browser sees your header, it will distribute that rule to all other users of the same browser. So all Chrome users will now suddenly be told to connect to your site purely over HTTPS. So make sure that your cert works before you do that. Now, the referrer policy, moving sort of from security into privacy. Referrer policy, I think, is interesting. Again, very underused, even less than content security policy. Why? We're all now supposed to be very aware of and cognizant of our responsibilities when it comes to privacy. We're adding these tools to sites that give users transparency over the data we collect, and the controls to turn certain behavior we're tracking on and off. What we haven't really thought about is the data that we're leaking from our website to third parties without meaning to in the referrer header. So the referrer header, as a reminder, this has been around for a really long time as well. It simply includes the URL of the page that you came from when you move from one page to another on the web. We used to use it all the time for analytics and tracking to analyze the paths that people take through websites. These days, we typically do that with client-side JavaScript, so there's really no need to track the referrer anymore. So like I say, I think like this is in an era of GDPR, it's kind of weird that we don't spend more time thinking about leaking data via the referrer header. So I would recommend that if you don't have one already, go and set a referrer policy and set it to the string origin when cross-origin. It's very unlikely to break anything, and it means that when you refer a user from your site to a foreign origin, the referrer header will contain only the domain of your site. It won't contain the full path, and it certainly won't contain the query string. The query string is where the real danger is, because let's imagine that your site is a contact database. So I want to search for one of my friends in my contact list. So I use your search facility and I put in my friend's email address. So I might then end up on a URL like example.com/contacts?query equals jeff@example.com. And so if I then click from that site to some other site, that email address is going to end up in the request. And you didn't mean it to, but it's going to happen anyway. So set a referrer policy, and then you can forget about it. If you're really confident that you're not using referrers for anything, feel free to set it to no referrer, and then you can get rid of the referrer header entirely. So, headers that start with access control are part of a specification called Cross-Origin Resource Sharing, or CORS. As JavaScript developers, probably you're pretty used to CORS at this point, because the ability to load data in the browser from data sources on foreign origins is really useful. And so typically we've all gone into a configuration somewhere and added an access control allow origin star header, or some code that will whitelist certain origins. There's actually quite a few CORS headers. The first one is by far and away the most common, but we also have access control allow credentials, which allows the browser to send cookies to the foreign origin. Max age, which gives us a TTL on these rules, and also expose headers and allow headers. Expose headers whitelists response headers, and allow headers whitelists request headers. If you are interested in trying to improve all of these things about your site rather than looking at them individually, feel free to go to securityheaders.io, bash in your domain, and it will give you a report that will look like this. And it will tell you, which headers you've got, which you haven't got, and which you should change. This is nothing to do with me. There is also another tool called Mozilla Observatory that does basically the same thing. So either one, Security Headers or Mozilla Observatory, are both great tools to use. So now let's talk about performance, and starting with client hints. Who's familiar with and used client hints before? Okay. Very, very few. And that's not really surprising. Client hints are really only a Chrome thing right now. But the idea is that you can send a response header with any response to the browser saying accept CH and then list properties that you would like to know about. And these are properties of the device, like device pixel ratio, the width of the screen, the width of the viewport, and whether or not the user has enabled save data mode. You can also set a TTL on that with the accept CH lifetime header, which I think is extremely badly named. Nevertheless, on subsequent requests, the browser will send you the information that you've asked for in individual headers. And this obviously means you can customize the response based on the capabilities of the device. If the device is extremely small, then you can send much smaller images. You can downsample the images to a lower resolution. One of the disadvantages of client hints is that it's not sent in the first request. So if you wanted to adapt the HTML page based on these properties, so say save data is set to 1, you want to send a light version of your HTML, you can't do it because the client hints are not sent in the first request. You'd have to redirect to capture the client hints and then render the page. I think that's a real shame, but you can use client hints to customize any of your subsequent responses, so anything that is a sub-request made by the page. Also, of course, you do get it on the first request if the user comes back to your site in the future. There are a bunch of new proposals for client hints coming down the pipe, so it's worth knowing about how the client hints framework works. So Mike West at Google, for example, is proposing that we add a client hint for user agent. This will replace the current user agent header. I think we can all see that there are a few minor problems with the current user agent header. And the idea is that this cleans up that data, it stops browsers from masquerading as other browsers, and it gives us some much more granular information on which to base decisions. Will this turn into the same bundle of lies that the current user agent header is? I don't know, hopefully not, but that remains to be seen. And also there's a suggestion that we replace the accept language header with a client hint as well. So, still on performance, the link header has been around since the dawn of time, and the purpose of the link header when it was originally conceived, I think even by Tim Berners-Lee in his original HTTP spec, was to link together semantically connected documents. So let's say you were on a chapter of a book. Then link headers would take you to the previous chapter, the next chapter, and the index. Now, we don't really use the web like that today, which is, I think, a bit of a shame. But we can use the link header to connect this document to other things, other URLs that are of interest. And one of the things we can do is list the URLs that we're going to need in order to build this page, i.e. resources, and most specifically, fonts. Because fonts are a big problem on the web. When in the process of rendering a web page do we discover that we need a font? It's not when we make the initial request, it's not when we parse the HTML, it's not even when we see that we've got a load of style sheet, it's not when we parse the style sheet, it's when we've parsed the style sheet, built the CSS tree, and seen that there's some text in that font on the page that needs to be visible. At that point, we'll start downloading the font. So, and fonts can be big, you know, so we need to get the font downloaded faster, and link preload is a really good way of doing that. This is a good example of the benefit that this can bring. This is a case study that Adi Osmani at Google did with Tinder. So you can see in the first screenshot here, we have a page that finishes loading at 200 milliseconds, but a lot of the JavaScript here doesn't start to be loaded until 1 second. In the second example, the page finishes loading at 200 milliseconds, and all the JavaScript starts loading at the same time. So this is the result of advertising to the browser in advance that you're going to need these resources. There's still a problem, though. In order to send headers, we have to tell the browser that this was a 200 OK, or a 404 not found, or something. You know, we have to know what the status code is. The result of this is that we can't do anything during the server think time. And this is really crazy if you think about it, because once we've received the HTML, suddenly the browser becomes incredibly busy. It's got to parse all the HTML, discover a bunch of resources, make like 100 HTTP requests all at the same time for all your images and style sheets and JavaScripts and everything. But just before that, there's a period of time in which the browser is doing absolutely nothing, because it has submitted the request for the web page to your server, and your server has not replied yet. And your server is really busy doing things like databasey things and authentication and templating and maybe some API queries. But that's not useful to the browser. So what would be nice is if we had some kind of new thing. And at Fastly, we're working on a thing called early hints, which is a new HTTP status code. There is actually already a mechanism built into HTTP that says that status codes in the 100 series are incomplete statuses. So they are to be followed later by a subsequent status. At the moment, that's only used for one status, 100, which is continue. But we propose creating a new one called 103. So how would this work? Well, your server would issue a response, HTTP 103 early hints, and would include some headers. And those headers would almost certainly be link rel preload headers. Later, once it's done all of its thinking and processing, and it's decided that the thing that you asked for is actually a real web page, it will then produce the real response. And it will probably include the same headers again. So doing this means that the browser can get going on downloading those critical resources whilst your server is still thinking about whether this request even makes sense in the first place. Because if it doesn't, and this turns out to be a 404 error page, then you probably still need the font, right? Because your error page probably is still styled and designed around the same theme as the rest of your site. So there are certain resources that you can almost guarantee that the page is going to need, regardless of whether that page even makes sense. So early hints is definitely not shipping anywhere as yet, but we are working hard, not just with browser vendors, but also with other CDNs to try and get this to be a real thing. Now, server timing is a performance header, which allows us to understand that period of time when your server is doing its thinking in more detail. You'll be familiar with waterfalls, the colored bars that you see in the dev tools that shows you the time that the browser spent doing DNS and TCP connect, request, and response, right? Now, sometimes that request line is really long because the server has spent a long time generating the response. But we don't know what the server was doing during that time. Well, the server timing header allows you to communicate granular details about how much time individual server-side processes took, and then it allows DevTools to render those as part of the waterfall view. Now, this is really primitive right now. This is the way that Chrome renders it. So you can see here I've created a request that takes a very long time to be processed on the server. Well, say very long time. It's still only 123 milliseconds. And then underneath those conventional statistics, we see a rendering of the server timing metrics over here. Now, one of the things that server timing can't do, it was designed to be very, very simple. I think it's a bit of a shame that it didn't go as far as doing this, but it doesn't include order. So it's not possible to say that, say, this pink operation happened before this yellow one. And it's not possible to say that they didn't overlap. So it's possible that this yellow operation actually happened inside of the pink one. But at the moment, all server timing is just a set of key value pairs that just give you timing information for operations. There is a JavaScript API, so you can pull this data out in your own JavaScript as well if you want to. Just as you can with the conventional timing data, that's also available in a JavaScript API. And I was using this and I thought, hang on a second. This might be the first time I've ever seen a JavaScript API into a dictionary stored in an HTTP header. I could use this for all kinds of things. Like, let's imagine that you are surfing a site that has a paywall, and I want to include the number of credits you have left on your paywall in the page. Well, I could store that object in a cache, like in Fastly or another CDN, and when the user requests that page, I could pull it out of the cache and add a header to it to say, this is the number of credits you have left, and then I could use some JavaScript to convert that into a simple key value map object. Kind of a cool idea. And I think this is possibly the only header that would actually enable you to do that via a JavaScript API. The problem with server timing is that there are certain metrics you might want to expose via server timing which you don't know yet when you dispatch the headers. So the headers have to be flushed to the network before the body starts to be streamed. But there are things like, how many chunks did you send in the body? How long did it take to send the body? What was the average data rate between the server and the client whilst the body was being sent? These are the kind of metrics that you couldn't include in a server timing header because you've already sent it. So what we really need is something that's not a header, but a trailer, and or also known as a trailing header. And believe it or not, this is actually really a thing, and was actually a thing for as long as headers have been a thing, but no one has ever implemented it. And the reason is because trailers actually have some quite annoying characteristics, one of which is that you could have any header as a trailer, and some headers affect the way that we render pages. So take content security policy, for example. If you were to put a content security policy in as a trailer, what does that mean? Like, because by the time we come to parse it, we've probably already made a bunch of requests which violate that content security policy. So it's kind of hard to grok, like, mentally how that would work. But server timing is a really good use case for trailers. So we've been working with Mozilla to get Firefox to support trailers. And I'm very pleased to say it now does. So if you it's specific to the server timing header, but if you have a server timing header and you send it as a trailer, then it will be parsed and made available via the JavaScript API in Firefox. And hopefully other browsers will do the same. I think the main issue with trailers was just the fact that it was general purpose, the idea that anything that could be a header could also be a trailer. Whereas if we just whitelist the ones that are not problematic, then trailers suddenly becomes quite easy to do. So I'd like to finish by talking about one of my one of my obsessions for this year, which is feature policy. And feature policy is a framework, kind of like client hints. The purpose of it is to control the behavior of the browser. So in the same way that content security policy will blacklist certain origins or only allow you to connect to certain origins, feature policy only allows you to use certain features of the browser. So this is a self-policing mechanism. It's a way to turn off large parts of the web platform, which makes your site inherently more secure. It's a way for you to police the activities of third parties that you load onto your page. So if you've got Disqus or Google Analytics or Facebook Connect or anything like that on your page, you might think, well, there's absolutely no reason why any of these third parties should be using the Web USB API or the geolocation API. So we'll just turn that off. This is how it works. You write feature policy, then you specify the policy name, and there's a directory of those policies, which I'll show you in a second. Then you have a list of origins that are allowed to use that policy. And the policies always define some behavior which you might want to turn off. So for example, autoplaying videos on page load. Who enjoys videos that autoplay on page load? No one? Great. So we could turn that off. Speaker defines the ability for the page to make a noise. So if you don't want your page to make noises, then you can turn that off as well. Or use self to restrict that capability to your own origin. And so on. On the left here, we have a list of policies which are currently kind of multi-party standards, so they're agreed at least between Google and Mozilla. On the right-hand side, we've got the ones that Google have shipped in Chrome, which is quite a considerably larger number. Don't take this as gospel. This changes all the time, and I captured this from a Chrome Canary with all the flags turned on. So this is very much in flux. But now is the time for us to get involved in this, because the thing that feature policy does, which all of you should be very concerned about, is that it takes web developer best practice and it bakes it into the web platform. What should be the maximum amount of script that you should load on a page? How long should you reasonably wait before rendering a web font? These numbers are starting to get baked into the web platform as part of feature policy. And so it is incumbent upon us, if we have an opinion on what any of these things should be, that we get involved in this effort and tell the spec authors what is reasonable. Because the people writing these specs are typically not web developers. They're typically working for browsers. This is the tightest feature policy that you could write today. Like I said, it would only work in Chrome. But this is turning off everything. And so I would suggest you take this feature policy, put it on your site, see what breaks. You'll probably find that quite a lot breaks, actually. Just for fairness, this is what happens when I did it to the Fastly website. It's pretty awful, to be honest. The logo doesn't show up. That's because our logo does not have a width and height attribute. And one of the feature policies called unsized media is the policy that allows you to have images that don't have width and height. So if I turn that off, then our logo does not display because it doesn't have width and height. We're also violating a policy called font display late swap, which means that our web font is taking too long to load. So that's why you're seeing the site render using a fallback font. And the reason you're seeing a bunch of JavaScript errors is because we load the JavaScript on the site synchronously, albeit at the end of the document, which was considered a best practice until very recently. But now that's not good enough for feature policy. It's saying, like, no, you can't load script synchronously. Even at the very end of the document, it has to be asynchronous. So it just doesn't load it. And as a result, a bunch of JavaScript, which is expecting those synchronously loaded scripts to be there, is erroring because it's not. So as a recap, feature policy, I love it, but it may also become your worst nightmare unless you get involved in the effort and start to define what it should and should not be. So please do. Content security policy, strict transport security, referrer policy, link rel preload, these are all bread and butter of the web. If you don't have them, you certainly should. And almost every site in the world will have a use case for them. Things like server timing and clear site data are a good idea if you have a use case for them. And then things like P3P, expires, Xcache, X-frame options via, and a bunch of other headers are cluttering up your responses, and you can probably get rid of them. And that all of everything that I've spoken about today, and a lot more, is on our blog. If you're interested in diving in more detail, farsi.com/blog/headers we don't want. That then links to the kind of the follow-up blog about headers that we do want. And that is everything I have on headers. Thank you very much.